Okay, so we're back to finish up talking about projectile motion. Last time we defined what projectile motion is. Essentially, it's two-dimensional motion when an object is in free fall. Okay, so it's moving both vertically and horizontally. We last time talked about how the two most important facts to know about projectile motion are the accelerations in each direction. In the x, or horizontal direction, the acceleration is 0 meters per second squared. In the y, or vertical direction, the acceleration is 9.81 meters per second squared towards the ground. Now, depending on your axis and which direction you want to be positive, that acceleration of 9.81 meters per second squared could either be positive or negative. Let's move to a little bit of a harder question now, involving something launched at an angle. A baseball is hit with an initial speed of 40 meters per second at an angle of 33 degrees from the horizontal. A, what's the maximum height of the baseball? B, what's the total time the baseball is in the air? And C, what is the horizontal distance that it travels? Again, our first step is going to be to draw a picture and label the positive directions. So here's my picture. Let's say this is my baseball. Okay, right when it gets hit, it has an initial velocity of 40 meters per second, and that's at an angle of 33 degrees from the horizontal. This is a horizontal dotted line. And since this baseball is going to travel up and then obviously back down when it's landing, this time I'm going to make my positive directions up and to the right. Okay? Now, could I make my positive direction down and to the left, or down and to the right, or up and to the left? Absolutely. But this is just what I'm choosing to do in this case. All right? So up and to the right are positive x, y, and x, respectively. Step 2, after you've drawn the picture, is to write down the x and y quantities separately. Remember, we have to keep them separate because they don't affect each other. Because they don't affect each other, you can't go plugging in an x variable in an equation with all other y variables. It will throw everything off. Okay? So all of our equations have to contain only x variables and possibly other, and only y variables or possibly other. Okay? Other can mix into either one. Let's write down what we know. The most important things that we know are the acceleration. In the x direction, the acceleration is 0 meters per second squared. In the y direction, the acceleration is negative 9.81 meters per second squared. Why negative? Because I know the acceleration of this object is towards the ground. That would be down. We said up was positive y. Therefore, a vector that points down would have to be negative. So this is now negative 9.81 meters per second squared. Again, if you wanted to say down was positive, there would be nothing wrong with that. You would have to switch some signs around, but you would still get the exact same answers. Okay? Let's see what else we know. Let's see here. I know the angle that's launched at, 33 degrees. Total time in the air, we don't know. Maximum height of the baseball, so maybe the dy max, in other words, the distance, the biggest y distance that it gets to, we don't know that. And we don't know the horizontal distance traveled. Okay, so that actually leaves 5 things that it looks like we don't know, but that's actually not going to be a problem because we can fill in every single one of those. We have to do so by thinking about the initial launch and its angle. Okay, if we think about this angle, we have a vector here, the initial velocity vector, that is not in the x or y direction. So in order to get this into the x or y direction, you have to think to yourself, I need to find the components of the initial velocity. Components can be found using sine and cosine. So I bring out my reference tables, and my reference tables say that to find the x component, I take the magnitude of the vector and multiply by cosine of the angle. So to find the x component, okay, the initial x component of the velocity, I simply do the initial speed, vi, multiplied by the cosine of our angle, theta. Now what is this equal to? vi is 40 meters per second. We're going to multiply that by the cosine of 33 degrees. Make sure you're putting the degrees sign, okay? I have to check for that. 33 times the cosine of 33 times 40 is 33.55 meters per second. I can do the same thing for the y direction, except in the y direction, to figure out the y component of the initial speed, I'm going to do the initial speed times the sine of theta. So that's VI times sine of theta, 40 meters per second, times the sine of 33 degrees, and that would be 21.79 meters per second. Okay? And it makes sense that that would be positive because the initial vertical component, the vertical component of my initial velocity is upward pointing. Okay? The ball gets launched upwards, and I said that was positive. Okay? So that's the representation of my initial vertical component of the initial velocity. Here's my x component of the initial velocity. All right? We can actually fill in the other three as well. Since the acceleration in the x direction is 0, I know that the final velocity in the x direction is the same as the initial because there was no change in velocity. So this is also 33.55 meters per second. I can't do that trick over here, but I do know a trick to tell both of these. When we first talked about free fall, we said that if something goes up and comes back down, at the very peak of its motion, at the very top, it is not moving in the y direction momentarily. So this Vy top, it's saying the velocity in the y direction at the top, that's actually 0 meters per second. Because at some point, the ball has gone as high as it can. It's not going up anymore, but it hasn't started falling yet. So the initial velocity, or the velocity at that point in the y direction, must be 0. Now here's a common misconception. People think, because they remember that at the top the velocity in the y direction is 0, and they assume that that means the ball completely stops moving, like no motion in the x direction either. Well, that can't be true, because in order for there to be no motion in the x direction, I'd have to have an acceleration to slow down the velocity, and that just doesn't happen. The acceleration is 0. So if something is launched in projectile motion, both vertically and horizontally, at the very top, the y velocity, the vertical velocity, reaches 0. The horizontal velocity doesn't change. It still is moving forward at that point. It just doesn't go up or down at all. So the vertical velocity is 0. There's even a trick for knowing what the final velocity is. This would be the velocity when the object makes it back to the ground, or just before it makes it back to the ground. Again, when we first talked about free fall, we said that if you launch something straight up and it comes back down, as it goes up and it passes a certain height, and as it comes back down and passes that same height, the magnitude of the speed is the exact same. So let's say let's say this baseball reaches a height of, 5 meters or whatever. As it goes up and passes 5 meters, and as it comes back down and passes 5 meters, the speed is the same at both points. The difference is in the direction. So we can apply this because if the ball was launched with this initial velocity right here, 21.79 meters per second in the y direction, right before it lands, it's going to have the same velocity. It's going to have the same magnitude of its velocity of 21.79 meters per second, but it's going to be negative because now the ball is headed back down, and we know that down is negative. Okay, so that's a couple of good tricks to remember. The vertical velocity at the very peak is 0 in projectile motion. The final velocity in projectile motion, as long as it's landing on the ground again, is the same as the initial velocity in the y direction, but with the opposite sign. And in the x direction, we have the velocity not changing because there is no acceleration. Now, you see, we got all this information just based on knowing the initial velocity and the angle that it's launched at. Now we can solve for the height of the baseball, the time that it's in the air, and the total distance. Let's solve for the height of the baseball first. I'm looking for the distance that it rises up. I don't know the time yet, so once again, any equation with time probably isn't going to be very useful to me. So I'm going to pick this equation again, Vf squared equals Vi squared plus 2AD. And since I'm working on the maximum height of the baseball, I need to use only the y variables. Okay, let's see. Since we're looking for the maximum height, this is the height at the very highest point. And at the highest point, remember, we know that the initial velocity is 0, or the velocity at that point is 0. So even though this isn't the final velocity down here that I'm looking at, okay, final velocity in this case just refers to some velocity at some point after the initial velocity, some point later on in time. So this, in this case, is really the velocity at the very top. We know that the velocity at the very top is 0, so I'm going to write 0 there. The initial velocity in the y direction, be careful, don't write 40. 40 meters per second was the velocity at an angle of 33 degrees. That was just the overall initial velocity. We need specifically the initial velocity in the y direction. We found the component of the initial velocity in the y direction. We found that to be 21.79 degrees, or 21.79 meters per second. So that is what I'm going to plug in, not 40, but the y component of the initial velocity, 27.79 meters per second squared, plus 2 times the acceleration in the y direction, negative 9.81 meters per second squared, times dy. In other words, the maximum height. And it kind of makes sense because what we're looking for here, if we say the initial velocity is 21.979 in the y direction, and the final velocity in the y direction is 0, we are measuring from when the ball gets launched to when it's at the peak. And this equation will help us tell what the distance the object has traveled is between these two velocities. So I do my math. I do 21.79 squared. I'm going to subtract that to the other side, so 474.8041 equals 2 times 9.81, negative 9.81 is negative 19.62 dy. Now I just divide negative 19.62 by negative 19.62, and I get that dy is equal to 24.2 meters. Okay. Notice that came out to be positive, which makes sense because the ball's maximum height is above where it started. And since it's above where it started, that's the positive y direction. Okay? Makes perfect sense. So that's the maximum height of the baseball. Now we want to find the total time that the ball is in the air for. Again, there's a couple different ways that we could do this. I think probably the easiest way to do this would be to use the Fiat equation. Again, in the y direction, because time depends on the y direction. Most occasions you're going to use time, or the y direction, to figure out the time. So here's what I'm going to write. VFY equals VIY plus AYT. I'm going to show you two different ways to do this once again. VFY, in this case, let's make this the time, or this velocity when the ball comes back to the ground. That's, according to this, negative 21.79 meters per second. If you get confused and you don't remember how we got some of these numbers, I encourage you to go back in the video and look at them. The initial velocity was 21.79 meters per second. Notice the difference in signs. Plus, the acceleration is negative 9.81 meters per second squared multiplied by the time. Now, if I want to solve for the time, watch what I have to do. I have to get t by itself, which means I have to subtract 21.79 over to the other side. Don't make the mistake of thinking that these are going to cancel out. Watch what happens. If I do negative 21.79 minus 21.79, it gives me negative 43.58. Okay, it doesn't cancel out to be 0. You're subtracting from a negative number. You're going to get an even bigger negative number. Now I just divide by 9.81. And the time, negative 9.81, the time comes out to be 4.44 seconds. This ball was in the air for a little bit under 4.5 seconds. Let me show you another way that you could get the time, also using the Fiat equation. Let's say you didn't remember this trick. You didn't remember that the final velocity in the y direction is the same as the initial velocity, but negative. Let's say that all you could remember was that the velocity at the very top was 0. Okay? So this time we're going to treat VFY as if it's the velocity at the top. I'm going to cross this off and write 0, and I'm going to plug in my initial velocity in the y direction, 21.79 meters per second, plus a negative 9.81 meters per second squared, multiplied by the time. I'm going to subtract 21.79 over to the other side, and then divide by negative 9.81. So it's a negative 21.79 divided by negative 9.81. I get a time of 22.22 or 2.22 seconds. And you might say, wait a sec, that's not the same as this. Well, of course, this is only the time for the object to get launched to go up to its peak. One of the things we said about projectile motion and free fall is that objects take the same amount of time to fall as they do to rise. This is only the time to get to the highest point, to rise. In order to get the total time, I need to incorporate the time that it takes to fall, which is the exact same. It's 2.22 seconds. So if I multiply this by 2, I get my exact same answer. 4.44 seconds is the total time. Okay? You can use either one of these methods, whatever you like best. Okay? Either of these will work just fine. You can either remember the final velocity at the ground and use that, or find the time for the ball to go halfway in its total motion. So basically go from the ground to its peak and then multiply the time by 2, because the time should be the same for the object to go up and to come back down. The last part of this question is, I guess I'll fill this out. So 4.2 meters. This is 4.44 seconds. The last thing I'm going to find is the horizontal distance traveled. And this is just like in the other example. Horizontal distance traveled, dx, since we're talking about horizontal distance, I have to use the x variables, equals vix times t plus 1/2 ax t squared. I have to use this equation because as soon as I tried to plug into the other equations, I wouldn't have a variable to solve for anymore. I wouldn't have a d to solve for, okay? Because it would cancel out. I know that the acceleration in the x direction is 0, so this term cancels out, leaving me with dx equals vix, the initial velocity in the x direction, which is 33.55 meters per second, multiplied by my time of 4.44 seconds. So dx equals 148.962 meters. Okay, a little bit under 150 meters. By the way, if you're a baseball fan, this is almost definitely a home run. I don't know of any ballpark that has an outfield that is longer or farther out from home plate than this. Just to show you that you could use another equation to do this, imagine if you did the average speed in the x direction equals dx over t. Average speed in the x direction, if your velocity is always the same, then by default it must also be your average speed. That's not always true, especially that can't be true if you're accelerating, but it's definitely true if you're not accelerating. 33.55 meters per second equals dx times 4.44. We're doing the exact same operation, so we get dx is 148.962 meters. Okay. Again, notice that we never mixed up our x and y variables. Oh, I gotta bring this up for you guys. Another thing to notice that's very important to notice is that once we split our initial velocity into components, we never used that 40 meters per second ever again. Once we got our initial velocity in the x direction and our initial velocity in the y direction, check my work, we never plugged in 40 down here. The only reason that we needed to know 40 and have this angle of 33 degrees was to find the components of the initial velocity in the x and y directions. So that's very important. The first thing to do if you're given a projectile motion question with something getting launched at an angle, you need to find the components of the initial velocity. That's the very first thing that you do. If something's getting launched horizontally, like in our other example, you don't really need to do that. But if something's getting launched horizontally, that is step number 1. I think I'm going to make one more video on this on the back of these notes, just as kind of like just as a practice for you guys to look and see what I'm doing and see how this works. So I'm going to stop this video here. I'm going to do one more, and then we're going to just practice a lot with projectile motion until you're comfortable with it. Okay? I'll see you later.